Alright, so greetings and welcome to week 11. Today we'll be discussing few questions on Nyquist criteria and all. So let's get started with first question. Here we have to consider is my screen still visible? Yeah, okay. So we have to consider a unity negative feedback closed loop system whose open loop transfer function is given. So uh, open loop transfer function g of s h of s is given as 2 in bracket s plus 8. Okay, so what are the open loop poles? That will be the roots of this polynomial. So this would do. So poles are minus 8 and 1. Now what is the closed loop transfer function? It is given by g of s h of s over 1 plus g of s h of s. So s square plus 7s minus 8 plus 2s plus 16, that would be 2 in bracket s plus 8 over s square plus 9s plus 8. So if we do closed loop poles, there would be roots of s square plus 9s plus 8 equals to 0, s plus 1 and s plus 8 would be two factors. So closed loop poles will be minus 1 and minus 8. Right, so here this open loop system is unstable, and the closed loop system is stable. So let's see, for this third part, uh, we want to see the Nyquist contour in the GS plane, and we have to check how many times it encircles this minus 1 point. So uh, the number of open loop poles These are two, right? And of which one is in RHP. And number of open loop zeros in RHP is 1. Sorry, in RHP is 0. So S plus 80 equals to 0. So S would be minus 8. So it is in LHP. So NC, that is number of zeros minus number of poles in RHP, that would be 0 minus 1 equals minus 1. So the Nyquist contour would encircle the point minus 1 once in the counterclockwise direction. So in second question, we are changing the plant transfer function to be this way. So let's consider unity negative feedback. So poles will be the same because denominator polynomial is same. So poles would be mm, s square plus 7s minus 80 equals to 0. That means s is equals to minus 1 and plus 8. So if we consider this previous problem, we had a open loop transfer function of this in the numerator. So if we say that s plus 8 turns out to be part of the controller transfer function c of s, so we would end up getting the same transfer function. So consider, as in problem 1, c of s to be s plus 8. Then g of s into h of s, this already means h of s is 1, would be equal to c of s into p of s into h of s, which is s plus 8 over. So if we write an equivalent closed loop transfer function, which we had found out in the first question, it would turn out to be 2 in bracket s plus 8 over s square plus 7s plus 8, which was stable. So if we consider this kind of structure as a transfer function, then it has a structure of Kp plus Kd into S. So this is like a PD controller. So just by using information from problem 1, we can say that a PD controller would stabilize the given current. All right. So that's yeah, that's the second question. Let's move on to the third one. Here, one information is slightly missing. So we'll assume that uh, the number of open loop zeros in RHS is zero. So if we assume this, we are expecting a causal LTI system. That means the degree of numerator polynomial is smaller than the degree of denominator polynomial. That also means the current output of the system does not depend on the future inputs. So whose open loop transfer function has two poles in RHB. So two poles in RHB. From the plot of open loop transfer functions contour corresponding to the Nyquist contour, the corresponding negative feedback closed loop system will be stable only when the -1 point is encircled how many times and in what direction. So we'll do NC as Z minus P. So that would be 0 minus 2. So that is minus 2. So we are encircling -1 twice in the counterclockwise direction. All right. So I think we can move on to the next question. Consider a unity negative feedback closed loop system whose open loop transfer function is given here. So g of s, h of s is given. So the closed loop transfer function would be s plus 4, and we'll have, sorry, yeah, s square plus 2s from here and 1s from the numerators. So 3s plus 4 in the denominator. So we are asked various gain crossover frequency, phase crossover frequency, and so on. So let's write the closed loop transfer function and get started. So let me call this closed loop transfer function as g of s, contrary to what we have been doing. So this I'll write s as j omega because now we are interested in the frequency response. So j omega plus 4 divided by minus omega square plus 3j omega plus 4. So if I were to write it, okay. All right. So let's take the magnitude. Let's rationalize this. So all right. So let's multiply. So is this fine? Okay, great. So, so we have minus 4 omega square and plus 3 omega square. So we'll have 16 minus omega square and then minus j in bracket. We have 12 here. Sorry, will it be? Let's see. We have, yeah, plus, correct. So j in bracket 12 and 4 would be 16 omega minus 1 omega cube. Okay. So now that we have it, we can find the gain crossover frequency. So, okay. So, what is the gain crossover frequency? It is the time at which, okay, let me not call it G because it's kind of misleading here. Let me call it some Z instead, because for calculating gain crossover frequency, we will not be using the closed loop transfer function, although it's still good to have some. Yeah, so the gain crossover frequency is when the magnitude of open loop transfer function happens to be 1. This implies, yeah, this is our open loop transfer function. So S plus 4 and S square plus 2. Alright. So if we put j omega g, so it will be j omega g plus 4 divided by minus omega square g plus 2 into j omega g. If we take magnitude of this, it should be 1. So if we take magnitude of, it will be under root 16 plus omega g square in the numerator and alright. So we want this to be 1. So if we square on both sides, we'll be left with, and if we omega power 4 g plus, so we'll have 4 omega g square and 1 omega g square will get subtracted from the other side. So 3 omega g square minus 16 equals to 0. So if you take x as omega g square, this is x square plus 3x minus 16 equals to 0. We'll get two roots from here. They turns out to be 2.772 and minus 5.772. So this root has to be rejected because x has to be positive. So omega g square is this, and if we take square root, this says omega g is approximately 1.665 radian per second. So we have found the gain crossover frequency. So now we are to find the phase crossover frequency. So we have g of j omega h of j omega equaling j omega plus 4 and minus omega square plus 2 omega. So 2j omega. This is for the numerator term, the j omega coefficient divided by constant term, and now the denominator. This will be, oh, we can factorize these into two terms. So j omega and j omega plus 2. So here the angle g of j omega, h of j omega, never reaches minus 180 degree. So no crossover. Now we have to find the phase margin and the gain margins. Phase margin is how much phase we are left with after when we reach the crossover frequency, that is omega g. It is given by 180 degree plus angle at omega g. So we can use this expression and substitute omega g equals to 1.665 radian per second to get 180 degree plus tan inverse of 1.665 by 4 minus 90 degree minus tan inverse of, this turns out to be 72.8 degrees. Now we have been asked about gain margin, but since there is uh, no crossover happening, this means that uh, gain margin is infinity. So the gain margin is found at that omega where the crossover happens or the angle reaches minus 180 degrees. Now we are asked the closed loop poles corresponding to open loop transfer function uh, given in problem 6R. So here Oh, pardon my numbering. This turns out to be number 6. So, so the closed loop transfer function is given here. Poles would be the roots of s square plus 3s plus 4. Okay, so let's so roots of this would be s is equals to minus 1 and wait, hold on. So, yeah, okay. So closed loop poles we have. Consider the closed loop transfer function, uh, closed loop sinusoidal transfer function corresponding to this problem, and we have to find its we have to find the low frequency value of its magnitude in decibels. So this is what we had found as the closed loop sinusoidal transfer function. And if we take its magnitude, that would turn out to be so. Alright, so to find the magnitude, we'll take limit omega tending to 0. Yeah. So what would this be? Under root 16 in the numerator and under root 16 in the denominator. So closed loop, this is 1. So if I take log of this, this is the magnitude in decibels. Now we have to find two more things. The slope in dB per decade of the high frequency asymptote and the cutoff frequency. So If we take two portions, s plus 4 and 1 divided by s square plus 3s plus 4. So here, so the magnitude plot would look something like this for this case. And here, uh, since this is a quadratic term, the high frequency component would be minus 20 dB per decade. So if we have to find the slope of high frequency asymptote, this will be, sorry, this is minus 40 since it's quadratic. So plus 20 minus 40, that would give us minus 20 dB per decade. Now finally for the last part, for cutoff frequency, we equate the magnitude to minus 3 decibels, which turns out to be 0.708. So if we solve this equation, we'll get 16 plus omega square equals to 0.708 whole square in bracket 9 omega square plus 16 minus 8 omega plus omega square. So if we solve for omega, this will turn out to be 2.13 radian per second. So this is the last bit. Hmm. Yeah. Do you have any questions, or do you want to move on to MPC? Okay. Let me write on a new page and just give a quick introduction to model predictive control. All right. So the idea of MPC is simple. We use a model to predict the system behavior and calculate a control input so that the desired output is obtained. Okay, so MPC problem has three elements. First is a model. Second is so three things I would like to explain: use of model. Second is notion of horizon. What does horizon mean in this context and all? And third is optimization. So we are using optimization to, in a way, to formulate the problem. We are using model for prediction, and the idea of horizon is something which tells us up to what limit or up to what time in future we are going to predict. So a time up to which we want to predict or compute. Loosely speaking, so we have two kind of horizons. First is prediction horizon, and second is control horizon. So say you are standing here at time k, and you'll use your model to predict at k plus 1, k plus 2, and so on up to k plus p. So this p is your prediction horizon, and say you are at k, so you are looking up to some time in future c, which we can call as control horizon. So you will get your input uk plus 1, and so on up to u k plus c. So what you do is, you want you are asking yourself a question. I have a desired uh, a reference, say yref at k, and say even if you can have it at k plus 1, and so on up to k plus p. If you have if you are getting it from a planning kind of an algorithm or a methodology, you can have it up to p, or you can hold it constant. So you have reference values, reference outputs, up to p, which you want to track. So you are asking a question: what should be my series of control inputs? Okay. So for which we will use a model for the system. So let's say that you have a system governed by xk plus 1 equals to axk plus buk, and you have yk equals to c into xk. So this is a discrete time state space model. which you want. So you are formulating your optimization problem as minimize yk plus I minus yref k plus I. So, so this is the error at any given time I, right? And this is the 2 norm of it. And if you do summation from say I equals to 0 to your prediction horizon P, and you want to minimize this. So in minimization, you will have a vector U, which is input vector made of uk, uk plus 1, and so on up to u k plus c. So up to c, up to k plus c, which is your control horizon, you will have different values of input. After that, you will hold it constant. So you say, I will plan my next, I want to reach somewhere, say y ref, in 5 time steps. I am going to plan my next 3 moves and I'll hold my third move constant so that I reach where I want to go. So that is, this is up to prediction horizon, and this is up to control horizon. So if you solve this optimization problem using any method, you can end up, so the solution of this, mm, say u star, you will obtain. So what you will do is, in this u star, you will pick u star k and implement it. So at each time instance, the optimization problem is solved, and the first control input is implemented. So here, yeah, this thing comes from the model. That is one brief overview of model predictive control. Okay, so in summary, we are using model to perform predictions, and in possibilities of control input which you can give, you are finding out that inputs called optimal inputs in this particular case because we are solving optimization problem, so that the reference and your model output matches. So I think, yeah, that's all I wanted to discuss for today on MPC. If you have any questions, you can ask. Okay. Okay, we'll take it off. Thank you. Thank you for joining. See you.